The third lecture in the limits portion of this class is on the algebraic properties of limits. I decided to try a different format with this lecture and use a narrated PowerPoint presentation rather than a chalkboard lecture. Let's see how it goes. This lecture is quite technical. There's a lot of algebraic rules. There's no pictures. And sometimes the motivation behind these rules can be a little bit lost. So I want to make it clear that the following theorems are proved using a precise definition of limit. Again, I mentioned this in the previous lecture. We might talk about this at the end of the year, but it's not really part of Calculus AB curriculum. Proving all of these results come from going from basic axioms, definitions, and just using logic. That's kind of the foundation of all modern math, and especially calculus. But again, that's a kind of advanced branch of math that you might see in college if you become math or science major. We'll use all of these following results without any proof to justify our techniques of calculating limits by hand using algebra. So without further ado, here are the theorems. First, we just want to say that some simple parent functions have easy limits. If you have a constant function, well, the function is always equal to b no matter what. As x approaches c, b stays close to b. So, okay, that's an easy limit. Almost as easy if you have the identity function, f of x equals x, then again, it almost doesn't need, this is not an axiom, this follows from the definition of limit, but it almost doesn't need to be proved that as x approaches c, x approaches c. And then some of these transcendental functions, again, these would take a little bit more work to prove these statements, but for this class, we can take it for granted that the transcendental functions sine x and e to the x, those can evaluate limits just by plugging in the value. As x approaches c, sine x approaches sine c, and same thing for exponential. There are a lot more parent functions than just those listed on the previous slide. You might have noticed, or might have even talked about in your pre-calculus class, the fact that most of the other parent functions can be created from even easier parent functions by using arithmetic combinations. So for example, if you think about x squared, y equals x squared as a parent function, parent parabola, then, well, you can create a new function by multiplying together two old functions, and x squared is just x times x. So we actually don't need any more parent functions than have just been listed, but now we're going to look at how arithmetic works with limits. And usually it works in the most straightforward way possible. So in the following rules, a, b, and c can be any real number, and we'll talk about some special cases. And n is going to stand for a positive integer, a natural number. And suppose that f and g are any functions where we have a known limit value. Okay, so f approaches L and g approaches k as x approaches c. One thing we can do is take a linear combination. That's a fancy way of saying just add together the two functions with a coefficient. So if we have just a times f plus b times g, then that's a new function, and as x approaches c, that new function approaches the same linear combination of the limits of the old function. So think about some special cases here, and sometimes I think in your book the special cases are listed as separate rules. For example, if a equals 1 and b equals minus 1, then we have the limit of f minus g equals L minus k, and that might be called the subtraction of functions rule. We might also have the special case where b equals 0, and that might be called the constant coefficient rule. The limit of a times f equals a times L. We can combine all those rules into 1 and just call it the linear combination rule. We could multiply functions. Instead of multiplying by a coefficient, by a constant number coefficient, we could multiply two functions together, and the limit works just as you would hope for. Limit of f of x times g of x equals L times k. And this works for division as well, as long as you avoid, or you're really careful about the special case of dividing by 0. You don't want to divide by 0 here. And again, if we use all of these rules, then just starting with the parent functions of f of x equals x, or the constant function, you can see how you can multiply such functions together, or add or divide such functions, and get any polynomial or any rational function. The last arithmetic thing we want to do is take an nth root, and once again, taking an nth root doesn't really affect the limiting process as long as you worry about the domain of the root. So if L is positive, n is allowed to be even. If L is negative, n can't be even. You can't take an even root of a negative number. Otherwise, the limit of the nth root of a function equals the nth root of the limit. In addition to the arithmetic operations, there are some special limit rules involving some other ways that we can play around with functions. So the first one is the composition rule. If you have a function g with a known limit, so g approaches L as x approaches c, and you have another function f which is continuous at L. So remember, I mentioned that briefly in a previous lecture. Continuous means that as x approaches L, f of x approaches f of L. So in this case, we can calculate the limit of the composition f of g of x by first taking the limit of the inside function g. Right? So as x approaches c, g of x approaches L, and then the whole limit is just f of L. So interesting to note that we need the limit to exist for both g and f. We need f to be continuous, but we don't actually need g to be continuous for this rule to always be true. And it's interesting to look at some special cases for why that is the case. Another rule, which when you read it and understand what it says, almost sounds really obvious, is if two functions are the same for all points on an interval, except for maybe at just one point, then they have the same limit. If a limit of f is L, then the limit of g is also L. It sounds really obvious. I mean, if you go back to the definition of limit, we said the limit doesn't care what happens when x equals c, only when x is near c. Well, if the functions are the same when x is near but not equal to c, then of course they have the same limit. And then the last rule, this one, visually, it makes a lot more sense, so I encourage you to draw a graph of this kind of situation. So consider three functions, h, f, and g, and they're always in the same order. So h is always the smallest, f is in the middle, g is the biggest. Okay, and that's true at least on some interval containing c, but again, it might not happen exactly at x equals c. Doesn't really matter what happens at that point. Suppose that the outside functions, so the smallest function h and the largest function g, squeeze together and actually have the same limit of L as x approaches c. Well, in that case, if f is squeezed between them, then f has the same limit as well. So again, this rule should sound pretty intuitive. It can be proved. We don't need to prove it, but we can use it. So now that we've seen all the rules, let's look at how we're going to use them to actually calculate some limits. The first rule is the almost any point rule. The first application is what I already mentioned in the slide explaining the rules. Because we can perform the arithmetic, as I mentioned, you can construct almost any non-piecewise parent function from pre-calc just by plugging into the using arithmetic, and then you can calculate the limit just by plugging into the function, as long as the limit point is inside the domain of the function. So just to give an equation for that, what I'm saying is the limit of f of x as x approaches c is f of c for a really wide variety of functions, almost all functions that you studied in prior math classes. If f is a polynomial function, rational function, a root function, an exponential function, any trig function, again, as long as c is in the domain, or any arithmetic or composition of the above. As long as there's no problem with the domain, you can find the limit just by plugging in. As long as there's no problem with the domain and no problem with a division by zero error, you can just plug in to find the limit. Here's one example. What's the limit as x approaches 2 of this crazy function, the of tangent 2x minus x to the fourth over 3x minus 1? Well, obviously, I have no idea what the graph of this function looks like, but when x is near 2, since all of these functions are just pre-calc functions, you know, tangent is sine divided by cosine. Sine was a parent function listed in my rules on the previous slide. Cosine, wait, I didn't talk about cosine yet. Oh, but cosine of x equals sine of pi over 2 minus x. And pi over 2 minus x, that's a linear function. And so cosine can be thought of as a composition of sine with a linear function. So that means that cosine is also continuous, just like sine. And tangent is just sine divided by cosine. So as long as cosine is not 0, and cosine of 4 is not 0. So in this case, again, I can, after applying all these rules multiple times, I can end up just plugging in 2 for x to calculate the limit. So this limit, plug in the 2 for x, tangent of 4 minus 2 to the fourth power, 16, divided by 5, and take it to the whole thing. The next rule, which I jumped the gun to talk about, is the all but one point rule. This rule, again, when you say it, it sounds obvious, but we have to say it to justify what we did in the first lecture, which was dividing out common factors to calculate a limit as we approach a hole in the graph of a rational function. So here's a rational function. Okay, it's already factored, and we can see that the x minus 2 should divide out, right? X minus 2 divided by x minus 2 equals 1, as long as x does not equal to 2. And so this original rational function equals just x plus 1 for all x in a neighborhood of 2, but not at 2. Anyway, the limits are the same, and they're both equal 3. So that's a good rule to know, and it works on more functions than just rational. For example, you probably saw this trick at the end of pre-calculus class. You can use conjugates to create a common factor and then divide it out. So you have this kind of function, x minus 1 over the square root of x minus 1. Okay, first of all, the denominator is not rational. We don't like that from a style point of view, and we found the trick: multiply by 1 creatively. So multiply by the conjugate, square root of x plus 1, divided by itself. And now the denominator becomes rational, x minus 1. And by good fortune, that x minus 1 is also a factor that occurs in the numerator. And so as long as x does not equal to 1, well, the function is just square root x plus 1. Okay, so if you want to take a limit as x approaches 1, now I can't just plug in x equals 1 into the function because I get a divide by 0 error. It has no value. 1 is not in the domain. But I can say that if x is not equal to 1, my function equals square root of x plus 1, and the limit is easy to calculate now. Now I can just plug in x equals 1 and find a limit of 2. We can use this divide out technique for simplifying trig functions as well. So if you have some difficult trig function, suppose your given function is this one, 1 minus tangent divided by sine minus cosine. Again, your first instinct is to plug in pi over 4, but you're going to get a divide by 0 error. Sine of pi over 4 equals cosine of pi over 4. So if you plugged in, you'd be dividing by 0. One way you can overcome this is to find a clever way, multiply the function by 1 creatively, cosine over cosine. And I'll skip some steps here. You should verify this on your own. The function simplifies to negative secant x. And now I can just plug in pi over 4 and find the limit of negative square root 2. The last rule we have was the squeeze rule, and this rule we don't really use very often, but there's one very important application, which is finding the limit as x equals to 0 of sine x over x. You might remember I used this function and looked at a table of values, and just from the table of values we guessed that the limit equaled 1. We have to use some analytic approach to verify that limit. You know, the graph or the table of values is a good way to get some intuition, but it's not quite a proof. And we can prove it using the squeeze rule. You have to find cleverly some functions which are guaranteed to be smaller and greater than sine x over x. Exactly how we do that, exactly how the squeeze rule is used here, and a few other examples of different creative uses of the squeeze rule to problem solve will be talked about in class, but I'm not going to put it into this lecture here.